I was building something the other day, and I had to give the guy at Home Depot the length that I needed in wood in meters, but I realized I had only measured it in centimeters, so I was like, oh no, what's going to happen? So I'm going to use my funny story about that and teach you about metric symbols. So look at this chart. You're going to have to copy it down in your notes, and I'm not really going to go over it because it's stuff you should already know. So just know that you need to pretty much memorize anything that's on this chart. You need to know that there are 1,000 milligrams in 1 gram, and you need to know that the symbol for gram is G. You need to know that there's 1,000 grams in 1 kilogram. You need to know that grams measures mass, and that these are the equipment that can be used to measure mass. And you need to do that for liters, meters, and seconds as well. So take a moment, read through it, study, memorize. Stuff you got to know. Next, briefly I'm going to go over how to measure using instruments. When you're measuring an instrument, you always have to read the smallest increment, that's the line, on the instrument, and then you're going to estimate the next digit, which is known as the estimated digit, and then you write in the unit. So I'll sample one for you, so no need to freak out. All right, let's say you want to measure liquid. Well, if you're measuring a small amount of liquid, always use a graduated cylinder because they have a lot more increments on them than a beaker does. Okay, so we see the increments are, the larger increments are in 5s, and the smaller increments are in 1s. So we're going to read the 1s. We look at the line. The line's curved, and liquids kind of do that. It's called a meniscus. It's whenever the line of the liquid curves down and it curves back up. Whenever you're reading a liquid and you see that meniscus line, you always, always, always read the very bottom of the line. Don't read in the middle or up at the top. Always read the bottom. So if I'm going to read the bottom on this, I see that it's at 12 milliliters. But my other rule was that I needed to estimate the next digit. That's called the unknown digit or the estimated digit. And in science, you just get that privilege. You get to guess what the next number would be. So we would say, this looks like it's right on the line 12, so I would say it would be 12.0 milliliters. You see how I estimated that next digit? All right, let's look at number 2 and do that one together as well. The big lines are in 10 milliliter increments, but you're supposed to read the smallest one, so let's zoom in. Okay, these lines here are, these small lines here are in 2s. So I'm reading, it's at 32 milliliters, but I always have to estimate the next digit. So I'm going to guess that it's at 32.1 milliliters, because it looks like it's just above that line. So I'll say 32.1 milliliters. Notice I always put the unit after all my measurements. So go ahead and do number 3 on your own. Stop the video. Do it on your own. If you're going to be measuring the volume of solids, and it has, 4 sides, and it's like a rectangular? Whether it's a rectangle or a box or a cube or something like that, then you just use your volume formula, which you have already memorized. It's length times width times height. But whenever you're measuring length or width or height with a ruler, you have to make sure that you estimate the next digit. So let's look at the ruler that was used to measure this box. Well, obviously this ruler was only, the smallest increment was in centimeters, and then they actually estimated the 10th digit there. So it was 0 marked on the ruler, and then they estimated that it would be 0.6 centimeters. Go ahead and calculate the volume out using your calculator. You're just going to multiply all 3 of those numbers together, and then that's your volume. And make sure you add centimeters to the end. If you have an irregular solid, so let's say I give you a piece of metal, and it doesn't have like 4 sides that we can usually measure with a ruler, you can use a way of measuring volume called water displacement. Again, it's probably review for some of you guys. To measure the volume using water displacement, you fill up a graduated cylinder with water. Okay, let's say you fill it up to the 10 milliliter line. All right. Then what you do is you add in your solid, and the water level will rise because you've added the solid. If you mark down what the volume was of the water alone, and then you added in the metal, and the water rose to 18 milliliters, I know that my volume of my solid was 8 milliliters because it rose the water that much. Now look at the volume of the metal in the example one. It actually didn't start at 10 milliliters. It started at 9, and then it rose to 18. So how much was the volume of your solid? It should have been 9 milliliters, so go ahead and write that on the side. Now, I kind of made a mistake. Did you guys realize what I said? 9 milliliters? Oh, I have the right number and I have the right units, but I didn't estimate the next digit, okay? So you would want to make sure you estimate your next digit, so it could be 9.0 milliliters. When you're measuring temperature or temperature change, it's the same thing as water displacement. You measure the temperature before and then the temperature after, and you can subtract it to find out your change in temperature. So using the thermometers on your notes, I want you to read the temperatures and come up with this temperature change. Be sure that when you're reading the temperature and you write it down, that you estimate that next digit. When you're measuring mass, we're going to use electronic balances in chemistry. And an electronic balance is really easy. You put the on button on and you use a balancing pan to put your chemicals on, because we never put chemicals directly on a balancing pan. There's a button on there that will either say 0 or it will say tare, and that means the same thing. It just means that it's going to zero out whatever is already on the weigh tray. So if I put a weigh tray or a balancing pan on the balance and I press 0, that means that it zeroed out the weight of whatever I put on it. For example, if I want to measure the mass of a liquid, I would put the beaker on the balance and then I would zero it out so the beaker acts like it's not being weighed at all. Then I would remove the beaker, add my liquid, and then put it back on the scale so that it's only measuring the mass of the liquid. How do you find the degree of precision for an instrument? Well, I kind of already talked about this a little bit. The degree of precision is just how precise an instrument is at measuring increments. So if we look at this measurement, it's 4.967 meters. Well, we know that 7 is an estimated digit because you always have to estimate the next digit. So that one, number 7, wasn't actually on your instrument. It wasn't on the ruler, it wasn't on the beaker or the graduated cylinder. So the last number that was on the actual instrument would be 6. So that is your degree of precision. The degree of precision of the instrument is the 100th place. Okay? The estimated digit is the 1000th place. Now look at the next number, 0.30 milliliters. Circle on your page the estimated digit, and now circle the number that shows the degree of precision of that instrument. Okay, you should have circled 0 for the estimated digit because the estimated digit is always the last digit. That's the one you guessed. And then the 3 is actually the degree of precision of the instrument. The instrument was able to measure to the 10th place of milliliters. Now let's look at this graduated cylinder. What is the degree of precision of this graduated cylinder? Look at the smallest increment. These increments are in ones. So the degree of precision is to the ones place. The estimated digit would be the digit after the ones. So the estimated digit would be the 10th place. Man, doing science can get you dehydrated, guys. Go ahead and stop the video and get yourself a nice, cool, refreshing drink. Okay, so I'm assuming you're back with your refreshing beverage. Let's go ahead and work on significant figures or significant digits. In science, there are two types of numbers. There are exact numbers and measured numbers. Exact numbers are known to be absolutely correct, and they're obtained by counting. So an exact number would be, there are 23 people in our class. There's no, I didn't have to measure that, it was an exact number, okay? Another exact number could be, if you're putting something on the electronic balance and it gives you a number, like it says, oh, this object is 10.56789 grams. But a measure number involves some estimation. Remember when I said whenever you measure to the smallest increment, that's the degree of precision, and then you always estimate the next digit. Well, significant figures are believed to be correct by the person that's making and recording the measurement. So what are significant figures? Or, as I like to call them, sig figs. We're going to talk about significant figures. Significant figures are the figures that you actually measure. That's why they're called significant, because you measure them. They're important to have. Alright, so if I give you a number like this, you would say that there are two significant figures. So one is significant and the 5, because I measured them both, right? So, but what if I gave you a number like this? How many significant figures are in this number? How many numbers did you actually measure? Well, in this example, I have a 0 and it's in the middle, but what that means is that when I was measuring the instrument, I purposely looked at the tens place and there were no tens. Okay, so it's 105. So I have 3 significant figures. That's my second rule. Embedded zeros always count. Okay, see how the 0 is embedded? It counts. So 1, 2, 3 significant figures. What if I had a number that was like this? Well, 1 and 5 obviously count because they're real numbers. This 0 is embedded. It's in the middle, so it also counts. I measured all these 3 numbers. Did I measure this number, though, or is it just a placeholder? Well, looking at our third rule, leading zeros, that means zeros in front, they'll never ever count. Okay, so this 0 is not a significant figure, so I have 3 sig figs in this example. Okay. Now, my fourth rule says that trailing zeros will count only if there's a decimal. Here's an example of a trailing 0 without a decimal. It means that I measured the 1, the 5, the this. We don't know that it was measured, so we say it's not significant. If there's a decimal, this is a trailing 0, and now it counts. Well, you might be asking me, what in the world is the difference between this and this? And why in the world does that even matter? Well, here's why it matters. If you told me, if you did an experiment, and you measured 150 milliliters of water, and you measured your instrument was at the tens place, that was the degree of precision, and you estimated the 0, then what you want me to do is to do the same thing. Measure, get an instrument that measures to the 10th place, and then estimate the 1. But if you don't put that decimal there, what it tells me is that this is not a number that you measured. Only these 2 are the numbers that you measured. So guess what I'm going to do? I'm going to get an instrument that measured to the hundreds, and I'm going to estimate the tens, but I'm not going to get an instrument that measures to the ones at all. See how that makes a difference? If you tell me, if you put a 0 here, it means I have to measure all 3 numbers. If you don't put a 0 there, that means I only have to measure these 2 numbers. And then start the video again, and then we'll try to do them together. Okay, let's do some of the examples in the notes. I gave you 325 milliliters. How many sig figs are there? Well, we know from our first rule, if it's not a 0, it always counts. So this would be 3 sig figs. How many sig figs are there? Well, all of these are not 0, so they all count, so that would be 4 sig figs. Now look at this one. How many sig figs are here? Well, remember our rule said embedded zeros count, so this counts, which means there are 1, 2, 3 sig figs. Now look at this number, 2309. Is this 0 embedded? Yes, so it was actually measured. So I have 4 numbers I actually measured. Okay, keep going down in your notes, and you'll see some more problems. Let's look at this number here, 0.01. How many sig figs? Remember the rule that leading zeros never count, so these don't count. The only one that counts is the 1. So it's 1 significant figure. What about this? Remember, leading zeros never count, so these don't count. This counts because it's not a 0. What about this N0? Does this N0 count? Well, let's look at our rule. Trailing zeros will count if there's a decimal. Is there a decimal? Yes, there is. So this 0 counts. We have 2 sig figs. What about this one? Leading zeros never count, so no and no. This is a non-zero number, so it counts. This is a non-zero number, so it counts. And this 0 is embedded. It's in the middle, which means we actually measured it. So it also counts. So I have 3 sig figs in this number. And it's going to ask you to round. So like if I give you this number, I'm going to ask you to round to 3 sig figs. Which of these is my estimated digit? This guy. So if that guy's my estimated digit, I have to, that means that's the last digit I can keep, and every other digit I have to get rid of. Well, you don't just chop it off and write that. You have to round, and so 5 or higher, I round my number to this, 53.6. I say round to 3 sig figs. 1, 2, 3. That's my last digit I can keep. So I look over at this guy. Is he greater than 5 or less than 5? He's less than 5, so that means I keep this guy the same. I don't do anything different. So it's 4.02. That's my answer. Okay, let me do one more with you guys. If I give you 12.367 and I say round to 4 sig figs, 1, 2, 3, 4, that means this is the last digit I can keep. I look at this guy. Is he greater than 5 or less than 5? He's greater than 5, so I have to round 6 upward. 12.37. And you're done skis, like me. Or my name isn't Dunsky. It's done. Have a great day.